All right, so today is a linear programming problem using Legos. We're going to be building tables and chairs, and the table is made out of 2 large Legos and 2 small Legos. The chair is made out of 1 large and 2 small. Altogether, we have 12 large and 16 small pieces. So the students in the classroom built the tables and chairs to find combinations. Profit for a table is $16, profit for a chair is $10. And we're going to find the product mix to maximize the company's profits. And so we came up with these combinations. The students built these to make sure that they worked. And there were some leftover pieces in most of the situations. So what we're doing right now is we're trying to determine the profit for each one. So far we got an $80 profit for 0 tables and 8 chairs, $96 profit for 6 tables and 0 chairs, $98 profit for 3 tables and 5 chairs. So we're going to move on to this one. 16 times 4 plus 10 times 4. Did anybody do this one yet? No? Okay, go ahead and calculate that one, please. I'll come back. What did I do wrong? No, 4 tables and, 6 tables and 1 chair. You don't think we have enough for that? All right, so 6 tables requires 12 large pieces, right? Yeah, I agree. I think that we don't have enough left over. Maybe somebody's bag had an extra piece in it. Because for this one right here, 6 tables is already going to use up the 12 large. So I think maybe somebody's bag had an extra piece in it. So we'll just take that one out. That's not a big deal. And let's do this one. 16. We have enough for this, right? 16 times 4 plus 10 times 3. All right, so how about this one first? 4 tables and 4 chairs. What was our profit? Did anybody put that in the calculator yet?
What?
16 times 4 plus 10 times 4.
Yes.
What'd you get? 104?
Yes.
All right, and how about this one? What do we get for this one? 94, thank you. All right, so looking at these, which combination gave the most profit of the ones we found? 4 tables and 4 chairs gave us the most profit. But we know that we didn't try all of the combinations out. There are a lot of different combinations. And so linear programming can tell us for sure what is the best combination. So we're going to go back and we're going to do the mathematical solution. We already know what X and Y are. We already know X is the tables and Y is the chairs. And the objective function is actually not graph. The objective function is the profit. And the profit in this case was $16 times the number of tables plus $10 times the number of chairs. So that's called our objective function. That one's not graphed. But we're going to turn the page and we're going to find the inequalities, and those will be graphed. Does anybody need a minute to finish this page? So for the large, we're going to talk about how many large pieces do we need in a table? You guys built them, right? How many large pieces did you need for a table? 2, good. So 2, and for number of tables, we're going to put, I think it's X, right? Yeah. 2X plus, how many large pieces do we need in a chair? Just 1, good. So 1Y is less than or equal to the number of large pieces we had. And how many large pieces did we have altogether? You can look in front of you. 12, right. We were supposed to have 12 large pieces. Okay, now we're going to write an inequality about the small pieces. So how many small pieces did we need for the tables? 2, right? Yeah, we needed 2 small pieces for each table. They were stuck together. Yeah, so it looked like 1, but it was 2 small pieces for a table. And then how many small pieces for a chair? It was also 2, right?
Yeah.
So the chairs and the tables had the same number of small pieces. And that's going to be less than or equal to the small pieces we had, but we had more than 12. How many did we have? We had 16, good. All right, so where it says additional constraints, this is talking about the fact that we can't do anything with negative Legos. We can't have any negative small pieces or negative large pieces. And so to account for that, we say that x has to be greater than or equal to 0. We can't have any negative tables, actually, in this case. And we can't have any negative chairs, so that also has to be greater than 0. And so we're going to graph the feasible region. Since I used pen, mine's kind of a mess. But we're going to also do this in Desmos, okay? So let's go to Desmos and let's graph these 4 inequalities. If you don't have that on your paper yet, please get that right now and then open up Desmos. All right, 2x plus 1y less than or equal to 12. 2x plus 2y less than or equal to 16. X is greater than or equal to 0, and y is greater than or equal to 0. Now, oh, that's a lot of color there. I'm going to try to make this one a lighter color so that I can see it better. I'm going to change it to orange. It's better. So there's an area called the feasible region, and the feasible region is the area that is can't see it. It's shaded with all of them. Okay, those are the corners of the feasible region. Now I'm going to probably on my paper, I'm going to graph all of these lines, but then I'm going to actually also graph the feasible region and shade it. So I'm going to use a pencil, and if you would like a ruler, I have some rulers here. I'm not going to pass them out, but if you want to get up and get a ruler, you may. Okay, so I have some rulers right here. Help yourself. I'm going to graph this first line that has x and y intercepts of 8. And then the second line has an x-intercept of 6, and it has a y-intercept of 12, so I'm going to graph that one. And I'm going to show you my paper. Okay. So I graphed the first line actually is the one that has a y-intercept of 12 and an x-intercept of 6. Rulers are right here if you want to grab a ruler. And then the second line has x and y intercepts of 8. And then x is greater than or equal to 0. That line is just right here on the axis. So I've got this one here. And I've got this one here. This is y is going to be greater than or equal to 0. And instead of shading each one individually, I'm just going to shade the feasible region. The feasible region is going to be in here. Okay? So I'm going to come around and see if you need any help with that. And I think I'll stay zoomed in on this. All right. So the corner principle says the optimal solution will always lie in a corner of the feasible region. So I've got this corner, this one, and this one. Does anybody think 0, 0 is going to give the optimal profit? Probably not, right? But I'm going to write it down. So 0, 0 is one corner point. The next one is 6, 0. 0.08. And this corner right here, 4.4. Okay, now we already actually calculated most of these profits, so we can copy them from the other side, but I do want to write out the equation. So the profit was 16x plus 10y. So first one, we got a profit of 0, which we're not surprised by because we didn't make anything. Okay, this is the 6 tables and 0 chairs. This one was the example on the front, and I think they said they got $96 out of that. Thanks. Okay, this is the one that one of your classmates came up with. 0 tables and 8 chairs. That gave us a profit of $80. And then the last one is the one that we thought might be the best one. Is it? Is this 104, did you say? Yeah. Yeah, $104. Okay, so it says which point gives you the largest profit, and so we found that that point was 4.4. How much was the maximum profit? How many dollars? Yeah, good. $104. All right, and then to maximize the profit, that means we should make how many tables? Right, this 4 means 4 tables. And then how many chairs? And 4 chairs. Well done. Okay, I'm gonna stop it there.